Okay, so today we're looking at condensation polymers. And the first thing to say about this topic is that it very much builds on two previous topics, which are carboxylic acids and derivatives and amines, and also very much looks forward to the next topic, which would be amino acids. So it's like a bridging unit, I guess, in a sense, between those two areas. If we look at what the spec says, the spec actually breaks down polymers. Well, it classes this section as polymers. I'm just going to focus on condensation polymers as opposed to addition polymers. We will just refer to the latter briefly. But it breaks the polymers, the specification breaks polymers down into two parts, condensation polymers, and then it's going to be about the sort of environmental side of things, so biodegradability. The vast majority of what we're going to do is this first section here. So one of the things to look at, if you look at the top, and it talks about the formed by reactions between, is we're seeing things that are both familiar and new. So we're seeing dicarboxylic acids, we're seeing diols, and we're seeing diamines. So we are familiar with the carboxylic acid functional group, we are familiar with the alcohol group, we are familiar with the amine group, but we're now looking at molecules that could feature two of those groups on the same molecule. And then the third bullet point here, the amino acids, that is something brand new to us. We're only going to touch on it because when we come to do amino acids, next time, in a sense, we will be starting from scratch, but we will be doing so with a recognition or referring back or thinking back to what we've done here in condensation polymers. If you then read the next paragraph here, it talks about repeating units, and then it mentions a polyester called Terylene, and then it mentions two polyamides, nylon 6,6 and Kevlar. And so we need to be specifically aware of those three polymers. And then typical uses, that's a really quite a straightforward thing and probably not something we're going to say very much about. I mean, that's something you can sort of read about yourself. And then we've got the student should be able to draw the repeating unit from a monomer structure, draw the repeating unit from a section of the polymer chain, draw the structure of the monomer or monomers from a section of the polymer, and explain the nature of the intermolecular forces between the molecules of condensation polymers. We're actually going to talk about this final bullet point when we talk about the environmental side or the biodegradability, because that's really, well, actually that's not solely where it's relevant, but that's where we can speak most usefully about it. And then the other ables too, they're going to be sort of implicit in the run through in the video. But what I'll do is I'll do a separate video where it's actual exam questions. So this is really just going to be, this video is really going to be about explaining or thinking about condensation polymers. All right, so the first thing to think about is, well, you have done polymers before. You probably did them at GCSE, and you probably also touched on them or did a bit on them when you did alkenes in the AS content. So they were always referred to as addition polymers because you were literally adding the monomers together and there was only ever one product. And remember, with an addition reaction, one way to recognize an addition reaction is the fact that you only have one thing on the right hand side of the equation, because whatever's on the left have been added together to make the single thing on the right hand side that they've been added. Now, condensation polymers have obviously that word condensation, and you may or may not be already familiar with what that's likely to imply. And needless to say, we're talking about a series of condensation reactions. But when we're talking about condensation, it is something that it's been referenced before. It's a reaction where a small molecule is lost. Now, that is typically water. So when people think about condensation reactions or condensation polymerization, they're typically always thinking about water because of that word condensation, but actually it can be other small molecules, and in fact one of the possibilities for us here is hydrogen chloride. So we've just got to be mindful that it's not automatically meaning water, although it's likely to mean water. So we're going to be looking at two types. You probably guessed that from the specification, but we're going to be looking at two types of condensation polymer. So we're going to be looking at polyesters and we're going to be looking at polyamides. And hopefully even from those names, you can get an idea, or you're getting an idea of the fact that we're going to be building on stuff we already know, because we have esters mentioned and we have amides mentioned. So we're now looking at those, the formation of those things, but obviously in a slightly different way. Now, if we think back to, or if we start with polyesters, sorry, and we think back to what we already know about esters, then hopefully you're going to recall that you could make an ester by reacting a carboxylic acid and an alcohol. And then we got an ester and water formed. That was a condensation reaction. That was also referred to as a condensation reaction. Importantly, it was an equilibrium reaction, so it was possible to reverse it based on increasing or decreasing the concentration of a reactant or a product, and that was a sort of, that's why ester reactions often feature in equilibria calculation questions. It's a way of bridging the sort of physical and organic side of the course. But it wasn't the only way we could make an ester, and the other way of making an ester was to use an acyl chloride and reacting it with an alcohol. Again, we got the ester, but this time the small molecule that was lost, or was hydrogen chloride. And so a couple of key things, or a couple of important things to remind ourselves about this, was that we would be able to recognize that hydrogen chloride was produced in terms of an observation, because it would produce misty fumes. So that's always something to make sure you've got there sort of lodged in your head. If they ever mention misty fumes, or they mention an acyl chloride forming ester and they're asking about an observation, just remember that's what you're going to get with hydrogen chloride. You also did that when you did the group 7 topic in the AS content, when you did the reducing power of the halide ions, so reacting a salt like potassium chloride or potassium bromide, potassium iodide with concentrated sulfuric acid. You had the different reducing power of the halide ions, but what you always observed was misty fumes or steamy fumes, and that would have been the hydrogen halide gas. The other thing to point out and stress when we're comparing the second way of making an ester with the first is that we mentioned about there being an equilibria in the first reaction, but the second one goes to completion. So if we were making a comparison between the first and second reactions, the second one has a disadvantage of producing hydrogen chloride, in the sense of it's a toxic substance. Please never use the word poisonous. Of course, we could use that hydrogen chloride usefully. We could make hydrochloric acid out of it, but often it's the toxicity we're thinking about, or the dangerous aspect of it. But the advantage of using the second one, the second reaction or the second method, is that we go all the way to completion. All right, we haven't got this equilibria where we've actually got a mixture of reactants and products. Okay, so that's just a reminder of what we know about esters already. And so now if we sort of take that and take it a little bit further and think about actually making polyesters. So we may have one monomer, we may have two monomers. That's an important thing to think about. So this is a difference with addition polymerization. With addition polymerization, you only ever had one type of monomer, or that's certainly what you focused on. So if you were making polythene, you had just ethene molecules as your monomer. And with polyesters, it could be that we have two monomers, or we have a single monomer, and we'll understand why that is in a second. So we're still going to start with two monomers, because that's probably going to be the most likely version if it's going to appear. I mean, we've obviously got to be prepared for both, but it's probably the more common version. And what we're looking at here is, and you'll now recognize these terms from the specification, is that we have two molecules, and they each have two of the same functional group. So we've got a molecule on the left there with 2 carboxylic acid groups, a molecule on the right with 2 alcohol groups. So we've got a dicarboxylic acid and a diol. We've got that letter N, as we've had with addition polymers. So that N represents a large number. So we don't specify how many of each monomer we've got, but we make it clear that it's a large number. And in this sense, in this instance, we're making it clear, that we're going to be involving equal numbers of each of those 2 monomers. And then they are going to react together, and they are going to form our polyester. So what we've got, say, if we just focus on this side here, we would have our ester or our esterification just like we would expect to when we did esters. But what we've got to realize is that can then take place at the other end of the molecule, and so repeatedly, right, and on and on and on and on. So we end up getting this structure, and I've just used the colors, the pink and the yellow, to just highlight which parts of this structure have come from which molecule. It's a condensation reaction. The small molecule we're losing is water, and then the number of water molecules we would lose would be 2n minus 1. So just to explain that, if we only kept the yellow and the pink, then you can see that we would be losing 2 H2O molecules. So we've got 2 hydrogens there, 2 hydrogens there, so that's 4 hydrogens, and we've got 2 oxygens, so that's 2 H2O. But the reason that it's minus 1 is that this chain will not go on to infinity, right? It's not never ending. There is a point at which there is, at one end of the molecule, still a carboxylic acid group, and at the other end of the molecule, still an OH group. And so that would represent 1 fewer water molecules being produced, or equate to 1 fewer water molecules being reproduced, and so we have this 2n minus 1. I've never seen a question, really. I can't remember seeing a question anyway with the 2n minus 1, but that doesn't mean it's not going to happen, so it's best to just be prepared for it. So that's how it generally works with 2 monomers. How could it work with 1 monomer? Well, here we have a single molecule where one end is the carboxylic acid and one end is the alcohol group. And so what it can do is it can form ester linkages with itself or with other molecules of the same type. So this sort of the carboxylic end with another of the same molecule could form an ester linkage with the alcohol end. This is classed as a hydroxycarboxylic acid. Again, I'm not sure that's something you need to be capable of naming, but it certainly doesn't do you any harm to appreciate that's what it is. So that, carboxylic acid is always your suffix in anything that you do at A level. Alcohols are your suffix if A is just an alcohol, or you can combine it with an alkene to have an N-ol. But if you have anything else like a nitrile, or you've got an OH group where you've got a nitrile or a carboxylic acid or similar, then the OH becomes is referenced through a prefix, and that prefix we use is hydroxy. So when you did aldehydes and ketones, and you did the nucleophilic addition reaction with cyanide ions, you produced a hydroxynitrile. So anyway, it's just to remind you about that. And then because this is a repetition of that single monomer going on and on, so this is a little bit more like how we've thought of addition polymerization, where we've had a single monomer. And again, we're going to have the -1 in terms of the water, because when at one end of this chain will be still an OH, and at the other end will be the carboxylic acid. So we will have the equivalent of 1 fewer water molecules being produced. So we've got our polyesters. So we just got ester linkage, and then at the other end ester linkage, and then at the other end ester linkage, and so on. That's hence the polymerization, many parts. We can make it with 2 monomers where we have a dicarboxylic acid and a diol. or we can make it with a single monomer if our monomer has both functional groups present. So here we've got the carboxylic acid end and the alcohol end. Okay, so it mentioned in the specification about Terylene, or also known as PET. So you actually might recognize it more from PET because that's often how it's going to be referenced in products and so on. You need to be aware of the monomers for this. So this is an application now of what we just saw. So it's two monomers. So that means one of them is a dicarboxylic acid, and in Terylene, the dicarboxylic acid is benzene 1,4-dicarboxylic acid. So that's what it's called, 1,4, because if we take the first carbon to be one of these, to be the carbon that one of these carboxylic acids is joined to, and then we count round 1, 2, 3, 4. Then the second carboxylic acid group is the fourth carbon away. And then the other monomer is ethane 1,2-diol. So the 1,2 is important because it is possible to have a diol with only two carbons where both of the alcohols are on the same carbon. So we have to make it clear they're on different carbons. They're on the first and the second carbon. And then, this time we're just making it clear. So you've got to think about the water being removed. So it's always the OH from the carboxylic acid and the H from the alcohol. And so we're just then sticking what's left behind together. I should have mentioned this on the previous slide, but do make sure if you're having to draw the structure like this with the square brackets, do make sure that your bonds, and this is the same with addition polymers, go through the brackets to show that there's a continuation. So that's at both ends. And also make sure that you show that your repeating structure is repeating n times. But that's Terylene. So that's a specific example of a polyester. Now, this isn't something that is it isn't part of the specification. That it's not something they test you on, right? This direction of the ester linkages when we have two monomers. But I want to show you it because sometimes you're having to work backwards. So and knowing this can help you, I think, work backwards. So far what we've looked at is we've looked at our starting monomers and then the polymer that they make. But quite often they will give you the repeating unit or the repeating structure. So like the product side of that, the equations we've been looking at, and they will ask you to draw the monomers. And I think if you're trying to spot quickly whether you're having to draw two monomers or a single monomer, I think one of the things to look out for is the direction of the ester linkages. If we look at the direction of ester linkages whenever we have two monomers, like we just did with the Terylene, what you'll notice is that those ester linkages are alternating. Right, so if you're reacting a dicarboxylic acid or a diacyl chloride, and I hadn't actually mentioned that up to this point, but bear in mind what we had said is how we could make an ester. We could make it with an acyl chloride. So we don't have to have two carboxylic acid groups. We could have two acyl chloride groups. It's the same thing. The only difference is that we won't get 2n-1 of water. We would get 2n-1 of hydrogen chloride. But anyway, if you've got two monomers, you're going to get an alternating direction of linkages. So, and I think that's a useful thing to just have an awareness of for when you're trying to work out the answer to certain questions. And that would also include the repeating unit and the repeating structures. So they would include two linkages, and that's another important thing, something to bear in mind. So what this would tell me is if I was having to break this apart and think about the monomers, I would, well, don't forget that when you made an ester, it was the carbonyl group of the carboxylic acid and the oxygen of the alcohol. If you're breaking a polyester apart or you're breaking an ester apart, you're breaking the bond between the carbonyl group and the single bonded oxygen. So this would be one of our monomers, not very well sort of circled there, and then the other monomer would be this plus the other carbonyl. I'm not sure, maybe that wasn't very well explained, but just bear it in mind. If you're seeing alternating linkages, you definitely have two polymers, and definitely think about that when you're either working backwards from your repeating unit or polymer structure, or if you're working forwards from your two monomers. If we compare that with a single monomer, like our hydroxycarboxylic acid, so this is to show that there is a difference. You'll notice that all of the linkages are in the same direction. So if you see the carboxylic, the ester groups, all of the linkages being in the same direction, so you can think of them like an L here, then that must have been a single monomer. And if you see them where it's almost like an L and then a mirror image of an L and an L and a mirror image, the alternating approach, then you've got two monomers. And again, if we're thinking about the repeating unit and the polymer structures, they will only show one linkage. So if all the linkages are in the same direction, you're only ever going to show one. And if the linkages are in opposite, alternating directions, then you're always going to show two. You're going to show both directions, as it were. So that was polyesters. So polyamides, it is exactly the same, right? They are identical, other than the fact that we're using a different, one of the monomers is different. So again, if we think about amides, we could have done it with a carboxylic acid and an amine. And that would have given us our amide and water. So again, it's a condensation reaction. We're removing a small molecule, we're removing water. Or instead of the carboxylic acid, we could have used an acyl chloride and an amine. So the amine's a fixed thing, just like the alcohol was a fixed thing with making an ester. Again, we're making an amide, but this time our small molecule that's removed is hydrogen chloride. The only other thing to mention, I guess, here is bear in mind that you would be expected in this second reaction to be able to draw the mechanism, the nucleophilic addition elimination. So they would expect that with the acyl chloride approach. But yeah, again, it's two reactions you've done before when you did carboxylic acids and derivatives. Again, just like with polyesters, we can have two monomers, or we can have a single monomer. And what is necessary is that overall we have two of the relevant functional groups. So again, we can have our dicarboxylic acid as we had before, and this time instead of having a diol, because we're making a polyamide, then we've got a diamine. But again, the principle is exactly the same. You're making the linkages at the end of each molecule. You're going to have two N-1 waters, because again, at the end of the very long polymer, there will be a carboxylic acid group, and at the other end there will be an amine group. So that's why it's -1. We're producing one fewer waters, but identical. And then we could have a single monomer, which if we're likely to get this in an exam, it will be an amino acid. So maybe you're already beginning to now realize why it's called an amino acid, because it has an amine group and it has a carboxylic acid group. Okay, so amino acids, the naturally occurring ones, there's only 22 versions, and really we'll focus on that. So but anyway, this is the idea, the principle behind this is an amino acid. So you've got your carboxylic acid group and your amine group on the same molecule. So it can react, it can form an amide linkage with another molecule that's the same, and so on. And so we get our polyamide, and again we get water. So fairly straightforward. Just bear in mind, just to sort of make it clear, this could have been an acyl chloride, so it could have been a diacyl chloride. I haven't seen it with an acyl chloride, on the single monomer, but it could be, right? It could be. So we just have to remember that that would mean that the small molecule removed would be hydrogen chloride and not water. But you can see it's so similar to the polyester. There are two polyamides we have to be aware of. So there's Kevlar. So you might have heard of Kevlar in bulletproof vests or in puncture resistant tires or stab proof vests. It's a very strong material, and we're going to talk in part about why it's so strong shortly. But here we've got benzene 1,4-dicarboxylic acid again, which was the same as Terylene. But this time our second monomer is a 1,4-diaminobenzene. So again, the same sort of principle on the numbering: 1, 2, 3, 4. Put those together, and that gives us our repeating structure for Kevlar. Condensation reaction. So this is just a concrete or specific example of the principle we saw on the previous slide. And then nylon, it's called nylon 66. Well, I'll explain why it's 66 in a second, but it's called nylon 66. We just commonly call it nylon. So we've got 1,6-hexane diamine, and then we've got hexane dioic acid. And it's called 66 because actually if you count the number of carbons in each of the two monomers, there are 6 carbons. So they're very clearly 6 here because it says CH2 6 times. Although that says CH2 4 times, don't forget we've got the carbons in the carboxylic acid group. So, and you can see in their names hex and hex, right? And hence that's why it's 66. And so there is the repeating structure. So I guess, you know, you can get this sometimes in the exam. You have to write this out. They probably give you the monomers, but you should remember them, I think. And the fact it's 66 as a nylon 66 is actually a helpful way of remembering it, because you know it's got to have 6 carbons, and it's just got to have the 2 amine groups and the 2 carboxylic acid groups. But one thing to bear in mind, if you do have to write the repeating structure or the repeating unit in an exam, is just the use of the brackets to make it a lot easier and a lot quicker. So remember, we've got CH2 repeated 6 times, so we've just put it in brackets and put a 6 after it. We've got CH2 repeated 4 times here, so put it in brackets and put a 4 after it. So just remember that. So those are our 3. We've now done the 3 specific polymers that they mention in the specification, and the Terylene or PET, Kevlar, and nylon 66. So we've done that. We've done dicarboxylic acids, we've done diamines, we've done diols, and we've done, albeit briefly, because we haven't done the topic amino acids, but we've done amino acids too. Just while we're on the amides, let's look at those directions of the linkages again, like we did with the polyesters. Let's see if the same thing is happening. So this is if we've got 2 monomers. So we've got our dicarboxylic acid or diacyl chloride and our diamine, and you can see again, just as it was with the polyesters, if we have 2 monomers, we've got alternating direction of linkages. So that means our repeating units and our structures are also show 2 linkages. So this incidentally is the repeating unit. So it doesn't have the square brackets as such. And then this is the structure. Okay, oh, and that's missing a bond, and I'll have to fix that. But obviously there should be a bond between that nitrogen and that carbon. Whoops. But anyway, you can see that we've got the alternating direction of linkages just as we had with polyesters. So that means that we should predict that if we have a single monomer, we won't have an alternating direction. We'll have the same direction of linkages. So let's have a look. So if it was an amino acid, and there's just, you know, sort of a made up, well, we've just got an R group because it doesn't matter what's in between the 2 functional groups. And again, we do have, like we had with the polyester, if it was a hydroxycarboxylic acid, we've got linkages in the same direction. So it's not they're going to ask you about the direction of the linkages in any way, shape or form, but I think your awareness or knowledge of it is going to help you when you're trying to decipher or think about answering particular questions where there are structures either that you've got to draw or you've got to work out the monomers from. And again, if it's the repeating unit, the polymer structure will only show one linkage. Okay. Just the other thing, I guess, to mention is in the exam, they don't necessarily, what's the best way of phrasing this? They don't necessarily show the repeating unit with, say, the nitrogen at one end and the carbonyl group at the other. They could have this NH here so that the repeating unit finishes there. So they could just sort of shift it along slightly. So I guess when you're doing practice questions, just, you know, you'll come across it, you'll realize whether it's what you're familiar with or not. So just be a little bit adaptable when you're writing, when you're trying to decipher a repeating unit. In terms of how you draw it, as long as it is genuinely the repeating unit, it doesn't matter whether you're starting with the nitrogen or starting with the R, as long as you've got all of the necessary bits in the right order. Okay. So that was condensation polymers, basically. There's one bit that I didn't mention, I haven't discussed yet, that was mentioned in the spec, and that was to do with their properties. And that's really because the reason for their properties is relevant to the reason for their biodegradability. So really, I'm going to talk about it here. But anyway, if we look at this, so this whole topic was actually called polymers, and then the first section was condensation polymers, and now this second section is biodegradability and disposable of all polymers. When they're talking about when we're talking about all polymers, we're talking about the polyalkenes, which are the addition polymers, the ones that you probably did at GCSE and that you definitely did in AS when you did alkenes. And then we've got the polyesters and polyamides, which we've just looked at. And one of those, the addition polymers, they're non-biodegradable, and the polyesters and polyamides are biodegradable. And one of the reasons, or the process by which they're biodegradable, is hydrolysis. And then the advantages and disadvantages of different methods of disposal of polymers, including recycling. I'm not going to talk about that. To be honest, it isn't really something that comes up much, but that, again, you've got to be prepared for it. But that's just something you can read about. That doesn't require me to try and explain anything. And then we have this: students should be able to, and they should be able to explain why polyesters and polyamides can be hydrolyzed, but polyalkenes cannot. So we will mention that. That's likely to be combined with a question about biodegradability or non-biodegradability, and the two combined together, you explain why one is or why one isn't. It would be something like a 2-mark question. Okay, so it's said in the spec about hydrolysis of polyesters and polyamides. This is what's going to allow them, or what does allow them, to be biodegradable. So we had hydrolysis when we looked at esters. Probably, I can't quite remember now whether it was ever explicitly mentioned with respect to amides, but the principle is going to be the same. So esters and amides, they can be broken down by hydrolysis, and that's what makes them biodegradable. And then, you know, as the spec said, polyalkenes, which are addition polymers, so polyethylene, polypropene, they are not biodegradable, and that means we can recycle polymers if we are able to break them down. Just to say about hydrolysis, the best way of thinking about it is to think that if you're adding water, that molecules can be split apart if you add water molecules. But anyway, it opens up the possibility of recycling polymers, as well as the fact that they're also not going to hang around in landfill sites for centuries and centuries like non-biodegradable ones will do. So just, I mean, this was also in the carboxylic acids and their derivatives. And when you looked at esters, obviously the forward reaction of making an ester was a condensation reaction. And here, you know, the making a polyester or a polyamide is a condensation reaction. It is water being produced, assuming it's not an acyl chloride. Obviously, if it was an acyl chloride, it would be hydrogen chloride. But the backwards direction, the backwards reaction is hydrolysis. So we're breaking with esters, it was breaking the ester apart back into carboxylic acid and alcohol. Here it's breaking our polymer back into the original monomers, which may be the dicarboxylic acid and the diol. Now, the reason that you can have hydrolysis with polyesters and polyamides is the fact that we have this carbonyl group, and we have a delta positive carbon. That's because that carbon is bonded to oxygen, and that oxygen is more electronegative. So we get a difference in the electron density. So just to remind ourselves about the definition of electronegativity, it's the power or ability of an atom to attract a pair of electrons in a covalent bond. So the oxygen is more powerful. It's better at attracting electrons, pair of electrons in a covalent bond. So you get these partial charges, delta plus, delta minus. And that's one of the things that we've learned when we've gone through the various families of compounds like haloalkanes and aldehydes, ketones, is that having a delta positive carbon can make or makes it that carbon susceptible to attack by a nucleophile. And remember, a nucleophile is an electron pair donor. Conversely, so it's not just about why polyesters and polyamides can undergo hydrolysis. We've also got to consider why it is that addition polymers do not undergo hydrolysis, and the way that we would refer to that is that they are non-polar molecules, or that their bonds are non-polar, and that means they are not susceptible to attack. So that nucleophilic attack is not going to happen. So we're not going to be able to break either the ester or amide linkages apart. So this is quite an important point to make, actually, and they do ask that question. So why is it possible to biodegrade polyesters and polyamides? Because they have a delta positive carbon in the carbonyl group, which makes it susceptible to attack by a nucleophile. Addition polymers do not, or are non-polar. Rather than saying they don't have a carbonyl, such they are non-polar, or they have non-polar bonds, so they are not susceptible to attack by a nucleophile. And then the last thing, which really is about explaining the properties that was mentioned in the condensation polymer part of the spec, but I think is relevant here, or it's good to do here, because in a sense it's repeating something that we've just mentioned with reference to why polyesters and polyamides can be hydrolyzed, and that's about why they have different intermolecular forces. So just like all molecules have van der Waals forces, all polymers have van der Waals forces, and because these polymers are very, very, very large molecules, those van der Waals forces will be strong. That explains why you can have ethene, which is a gas, and when you turn it into polythene, so it's the same it's the same atoms, but now they're all in a very, very long chain. We now have a very large molecule, so we now have very strong van der Waals forces, which is why then our product, the polythene, is a solid. Okay, so they have very different, ethene and polythene have very different melting and boiling points, and that's because of the sizes of the molecules. But what we've also got now with polyesters and polyamides is that we have further intermolecular forces. So with polyesters, we've got the carbonyl group, so we're going to have permanent dipole-dipole interactions. And with the polyamides, even stronger, we're going to have hydrogen bonds because we've got the nitrogen and the hydrogen, or hydrogen attached to nitrogen. So if we just show a polyamide, but bear in mind you could draw something similar for a polyester, and just obviously it wouldn't be hydrogen bonds. But you can see now there are a number of hydrogen bonds between the chains. So this is one polymer chain, this is another polymer chain. We have our delta pluses and delta minuses because of the differences in electronegativity. We've got hydrogen bonding because we've got hydrogen bonded to a nitrogen, and then it can form an attraction to a lone pair on an oxygen. And this explains, for example, why Kevlar is extremely strong. So the chains can get close together, they have strong van der Waals forces, but even more so, they have strong hydrogen bonds. And therefore, we're explaining the properties, the differences there. So typically, condensation polymers are stronger. I wouldn't say, I just got more rigid here. You can have plasticizers, of course, so let's just, I don't think the rigidity is quite so important in answering questions or talking about questions as the strength. But if we think about Kevlar, you know it, or probably have heard of it because of bulletproof vests or stab-proof vests or puncture-resistant tyres. And that strength comes from the fact that the intermolecular forces between the chains are much stronger than they are between, say, in addition polymers. I guess one thing to just mention here before we finish is that when you come to your final exam, you mustn't think of your content as being year 12 content and being year 13 content. I mean, obviously, up to as we're going along at the moment, that's sort of understandable, but they won't be thinking, the examiners won't be thinking like that. They'll be thinking of 2 years of chemistry. And so quite often what happens is that a fair amount of the content that you learnt in year 12 features in what you think of as year 13 content. So intermolecular forces, the question or the context might be, say, for example, condensation polymers. Just another very brief sort of type example, if you reacted but-2-ene with hydrogen bromides, and you drew the products, so that was very much an AS content. It was electrophilic addition, it was alkenes, but if you then drew the products, you would notice that the product was an optical, or would exhibit optical isomerism. It would form optical isomers. So, that would never have been mentioned when you did alkenes because you hadn't done optical isomerism. But that's not to say that type of thing couldn't feature in an actual exam question. So just be alive to that. Don't always be thinking rigidly about this is alkenes, this is alkenes, this is alkenes, or whatever. The exam questions they won't even always be just on one topic anyway. They'll feature a variety of topics. Anyway, I hope that was useful. The specification